Hey guys, so today is our third day. I started shooting this video over here. I hope this would be more helpful than or more clear than the last one. Okay, so today's our third day. Let's review what we learned in the lecture 2. So in the last class we talked about Archimedes' principle, right? So Archimedes' principle tells the magnitude of the buoyant force on an object is equal to the weight of the volume of the fluid displaced by that object when the object is in the fluid. Okay. We also looked at the equation F buoyant equal to rho fluid V fluid times Z, or something, at least in our equation we wrote like FB equal to rho F VF times Z. This quantity come from where? Mass of the fluid, right? So M times Z was the, and then this M times Z would give us the weight of the fluid that is displaced. Okay. So that is what we learned about Archimedes' principle. We also learned about ideal fluid, right? So ideal fluid has what? Ideal fluid, we are making some assumption about the ideal fluid, or we're saying what kind of fluid, what kind of character does the fluid need to have to be an ideal fluid, and this we use this for fluid in motion. Remember, guys? So for an ideal fluid, steady flow or laminar flow, meaning the velocity of the fluid particle at any point along the streamline is constant, right? An incompressible fluid, meaning we cannot really compress it, meaning we cannot change the mass. The mass won't change even if you compress, but the important thing is the volume doesn't change. So even if we compress the fluid, let's say water, we cannot really do it, right? If we try to compress it. So it means the density is constant because mass cannot be changed whether you compress or expand. However, the important thing is we cannot, for water, for water or anything, any other thing, even for air, right? You cannot change the mass even if you compress it. However, for air, the volume is different. So this part of this, fluid in motion, ideal fluid, we want this is not very good approximation for air. Okay. So incompressible fluid means the density is constant. We also assume our fluid is non-viscous, meaning it has no internal friction, so the energy is not lost basically. Okay, and we looked at the example of turbulent flow. Remember, like if you go around a river or rivulet, you see some part of the water is kind of flowing through like this, and then if you were to take up water flowing through a pipe, it would be something like this. So it has a steady flow. However, in the case of turbulent flow, the flow is not steady. Okay, so the water may be circulating, or they are changing their velocity. All right, so that was about the fluid in motion, or ideal fluid, and then we did that assumption to come up with the equation of continuity. So we looked at and we found out A1 times V1 equal to A2 times V2, which is equal to constant. So here A was cross-sectional area, right? So we made a tube something like this. We had the cross-sectional area. This is like a greater cross-sectional area A1, and then we looked at the smaller cross-sectional area A2. We looked at the velocity B1 here. We looked at the velocity here B2 of the particle. Let's just write V2, speed of the particle. So basically this object that's, so these fluids, right, depending, since this product of the area, cross-sectional area, and the speed is constant, so as the, this pipe gets narrow, or this tube gets narrow here, the speed of the fluid is going to be higher. Okay, that's the thing we looked at. And then this A1 B1 times A2 B2 equal to constant, and consequence of this was Q, where Q is the volume flow rate. So volume flow rate Q is what? Volume of a fluid flowing in unit time or per time. Okay, and we derive it Q equal to A times B. A is again area, B is the speed, and then SI unit of this quantity is meter cube per second. Okay, so that was about the continuity equation. Okay, so before I start putting this here, I want to ask you guys this question. What do you think would happen? Let's say, what do you think would happen? Like if we have the tube, just like in the case of, maybe not just like the case of the continuity equation, but what do you think? Do you think the pressure increases as the speed of the fluid decreases if you were to take a part of the tube? What do you think? Let's say that, imagine tube goes something like this. Let's see. If you have a tube, something like this. I'm going to exaggerate this here. And then it goes something like this. What do you guys think? What do you think would happen? Let's say you have cross-sectional area here. Let's assume this as A1. And then we have let's take this cross-sectional area. This should be start somewhere around the same point, okay? So let me make this little better. Okay. Let's say we want to take this, some cross-sectional area A1 here, and then let's take some cross-sectional area A2 here, okay? And then this velocity, fluid is going to moving with the speed B1 here, fluid, we'll talk about that again, B2 here. Let's say we have a fluid flowing through this tube. What do you think would happen here? Pressure, let's call the pressure here is P1, and then pressure at this point here is P2. How do you think this pressure changes, as we have the, here, we know from continuity equation this B1 must be smaller than this B2, right? Because it's at the wider side. What do you think would happen? How is this pressure change, Okay, so even the continuity equation talks about how the the speed changes as the diameter or as the cross-sectional area of the tube changes, but it doesn't really tell us why does that change happens, or really change in the speed means what, or at least here change really is the what, accelerating, right, the fluid. So why does the change happens? We don't know just from continuity equation. So in 1783 there was a scientist, Bernoulli, Daniel, let's look at him here. So Daniel Bernoulli, he lived from 1700 to 1782, he lived for 82 years. So, he was a Swiss physicist, and then so he came up with the equation called Bernoulli's equation in 1738, and this equation tells us why there is a change in the speed of the fluid, okay, when the fluid flows from wider part of the region in the tube to the narrower part of the region. Okay. All right. So okay. So Bernoulli's equation. So Bernoulli's equation relates the pressure in a moving fluid to the speed and height of the fluid. Okay. Again, we are going to make some assumption here. So the fluid is incompressible. Incompressible means what? You guys, I tell you guys right a few minutes ago. Incompressible means what? Can the mass change? Can the volume change? So there is no change in mass, no change in volume, right, basically. So incompressible means the density is constant. It's also non-viscous, so there is no internal friction, non-turbulent, so we are assuming the, fluid is not going like this, okay, not with the turbulence, okay. Alright, so let's do this equation here, Bernoulli's. I'm gonna move this away, guys. Okay. Alright, so I'm gonna draw it over here. Make a diagram over here. So please make sure when you are watching these, watch this video totally and then try to do it on your own, or if you are trying, you could also just, pause the video, draw what I'm doing here and then kind of go through the step, okay? But make sure you do it, don't sit there just watching the video and then not like a movie, okay? Because physics doesn't work like that, okay? You kind of have to draw it to make your mind remember it, okay? So alright, let's consider a tube.